Okay, gentlemen, we are moving on to 5.4. But before we look at 5.4, let's just do a quick review of some of our stuff with our logs and our exponentials. I'm going to leave the first two to you, and I'm going to jump down to h of x. Recall with h of x, we have our basic y equals e to the x graph. And we know that that graph has been translated to the right 1 unit. We know that that graph has also been flipped over the x-axis, and that this +1 tells us that that graph has been, every point has been shifted up 1 unit. So if we think of our basic e to the x, which would look something like that, and if we were to shift to the right one, our graph would be over here shifted, flipping over the x-axis and going up 1. And our graph is going to look a little bit something along these lines, and I'll fill in our numbers in a moment as we find the information about that graph. So we know with our exponentials, our domain is everything, -infinity to infinity. With our range, our graph has been flipped, so now our range is going from a -infinity up to that +1. Remember that value that shifts our graph up or down is going to change our range. And we know that our x-intercepts, we set y equal to 0. So if I set h of x equal to 0, I'm going to bring my e term over. And we know that if we're trying to solve for our exponent, we want to get like bases. And we know that 1 is the same thing as e to the 0. So we can set our exponents equal, and we get our x-intercept to be over here at 1, 0. And for y-intercepts, we know we always set x equal to 0. So if I set x equal to 0, I'm going to get minus e to the -1 plus 1. Or basically, that is what, 1 over e plus 1. And we know e is 2.7, so around a -1/3 plus 1 is going to be right around a +2/3. But we will leave it exact at -1 over e plus 1 as our y-intercept. And then we know with our exponentials, we have a horizontal asymptote, and that horizontal asymptote has moved over here to y equal a +1. Again, recall that your range and your horizontal asymptote should be in agreement based on that translation, that movement of your graph up or down. And let's look at a couple of just quick simplifies as a quick refresher here. Remember that logs are ways of expressing those exponents. So on number 2, the log of 81 base 3, we know that that's asking us 3 raised to what exponent gives us 81, and we know that it is 4. On the log of root 6 base 6, that's asking us 6 raised to what exponent gives us 6 to the 1/2, and we know that that is equal to 1/2. On the right here, the log of 1000 base b equal to 3. Remember that this is a log form, and we can switch it to an exponential form, which was just telling us if we take a base b, and we know logs equal exponents, so the 3 is our exponent, so b cubed equal to 1000, and if we take the cube root of both sides, we know that b would equal 10. And below here, again, going from a log form to an exponential form, we know base 2 raised to the exponent of 8 would give us our x, and 2 to the 8th is 256. And we'll do one more down here with our e. Recall that there is an e, base e, that is implied. And this is just asking us if we take e, which exponent do we have to raise it to get e to the 2/3? And we know that that is just equal to 2/3. And I will let you guys fill in the rest of those for some additional practice. And one last thing with our domain. Recall with logs, we have a restrictive domain. We can only take logs of positive quantities. We cannot take logs of 0, and we cannot take logs of negative numbers. So if we just look at the first one, we know that the quantity of 12 minus 4x has got to be greater than 0, or that 4x has to be less than 12, or x has to be less than 3. So our domain would be from a negative infinity to 3. On the next one, we're taking the log of x squared minus 25, so we know that the quantity of x squared minus 25 has got to be greater than 0. Recall that anytime you had a second degree or higher with an inequality, you would be thinking of a plus-minus chart. We also know what the graph of this looks like. We know we have x-intercepts at a -5 and a +5. We know that graph is opening up, that parabola. So when does this graph go above the x-axis? We know it goes above the x-axis to the left of a -5 and to the right of a +5. And we could have done a plus-minus chart as well to help us to determine that as well. And I will leave this last one here for you to do, but keep in mind you want that quantity that you are taking the log of to be greater than or equal to 0. And for your domain, you should get a negative infinity to a -5/4 and 1/2 to infinity. And I will let you work that one out, whether you, and recall you'll have to do a plus-minus chart there. So one last thing, the main thing with our exponentials and logs, okay, is remember that, and we're going to be working with b greater than 1. If we have f of x equaling b to the x, that our basic graph is this exponential that is increasing from left to right from quadrant 2 into quadrant 1. We know our domain is everything. We know our range is above 0. We know that our x-intercept does not exist. We know we have a y-intercept at 1. And we know we have this horizontal asymptote at y equal to 0. For our graph of g of x equaling the log of x base b, again, base greater than 1, our basic graph looks something along these lines, where our domain is now greater than 0, because logs, remember, we have a restrictive domain. Our range is everything. We do have an x-intercept with our logs, which is at 1. We do not have a y-intercept. That does not exist. And we have a vertical asymptote at x equal to 0. And if you remember just anything from Chapter 5, recall that your exponentials and your logs are inverses of each other. They are symmetrical over that line of y equals x. Okay, that is the relationship between those two. And then going back to Chapter 3, we know that if two functions are inverses of each other, then both of their compositions must equal x, right? Whatever you plug in when you combine a function with its inverse, you are going to get out, as long as that quantity is in your domain. So if our logs and our exponentials are inverses, if we plug the log function into our exponential function, then whatever we plug in, we are going to get out. But recall with our logs, we have a restrictive domain, so as long as we plug in x, we will get out x, as long as x is greater than 0. We can only use x values greater than 0. If we combine our exponential and our inverse, plugging in our exponential into our inverse function, then we know again, whatever we plug in, we are going to get out, and that is going to be equal to x, and that is for all values of x. Our domain, we have no restrictions with our exponentials. And we know taking the log of b to the x, that quantity is always going to be positive. So our domain there would be negative infinity to infinity. So on number 4, last little bit of our review. The log of b base b is always going to equal 1. Right? If I take b and I raise it to the first power, I am always going to get b. So the log of b base b is always going to equal 1. The log of 1 base b, if I take b, I know if I raise it to the 0 power, I am always going to get 1. So the log of 1, regardless of our base, as long as our base is positive, greater than 0, is always going to equal 0. And likewise, recall that if we have b raised to the log of p base b, again, plugging in our log into our exponential, whatever we plug in, we are going to get back out. We will always get that quantity of p. So if we look at this, our one example here, plugging in the log into our exponential, so 2 raised to the log of 8 base 2. Keep in mind, it was a base 2 exponential, a base 2 log. Those are inverses of each other. So we plug in an 8, we are going to get out an 8. Okay, so those are all things that we had talked about in 5.1, 5.2, and 5.3. So now let's look at some more properties with our logs that we will be working with in 5.4. So if you recall, logs are just ways of expressing exponents. So all of our rules with exponents are going to have to hold true with our logarithms because those are just ways of expressing exponents. So if we recall that with our logs, with our exponents, if we were multiplying two quantities with the same base, then we know that as long as we have that common base, we would just add those exponents together. Well, logs are just ways of expressing those exponents. So anytime you have a single log product with that one common base, in this case p, then that is the same thing as just adding those two exponents, adding those two logs together. So the log of the product PQ base B is equal to the log of P base B plus the log of Q base B. With our quotients, we'll think back with our exponent rules. We know that if we are dividing two quantities with a common base, then we keep that base the same and we just subtract those two exponents. Well, logs are just ways of expressing those exponents. Exact same situation holds true. If we are dividing, we have a quotient, single log quotient, then that is the same thing as 2 log subtraction. Single log product was 2 log addition. Single log quotient is 2 log subtraction. Multiplying, we know we add our exponents. Dividing, we should be subtracting our exponents. And lastly, keep in mind, think back to if you had a base with an exponent raised to another exponent. So we have a power raised to a power. Well, we know if we have a power raised to a power, then we should be multiplying those two exponents. Logs are just ways of expressing our exponents. Exact same rules hold true. So if we have the log of a quantity raised to a power, then we should be multiplying those two exponents, multiplying those two powers together. That's probably easier to see down here below. If I had the log of 5 squared, I know that that's the same thing as the log of, 5 times 5. And the log of 5 times 5, I know is the same thing, single log product. If I come back and just think over here, that's the same thing as the log of 5 plus the log of 5, which tells me I have one of these plus another of those. So I have 2 log 5s, which is the exact same thing if we had taken that exponent and just brought it down in front, and we would have gotten our 2 times the log of 5. Okay. And lastly, base changes. Most popular common bases are base 10 and base E. And we've seen that we've been working with lots of different bases, and sometimes we may prefer to work with one base over another, or we may want to switch something to base 10 or to base E. So we can do a base change. So anytime you do a base change, if you have the log of C, base A, and I want to switch base A to a different base, then that is equivalent to the log of C to that new base, base B, divided by the log of that original base, the log of A, base B. Let's look at a numerical example here. So the log of 8 base 2, we know it's 3, but let's pretend that we didn't. Log of 8 base 2 we know is equal to some exponent. Logs equal exponents. Recall, this is just our log form, so we can switch this to an exponential form. So I can think of this as 2 raised to the x is equal to 8, or 2 raised to some exponent, right, is equal to 8. And just like we can add 5 to both sides, we could divide 3 by both sides, we could square both sides. As long as whatever we do to the left, we also do to the right, we can take the log of both sides. And I am going to just keep with base 10. Recall, if I don't write anything, a base 10 is implied. So the log of 2 to the x equaling the log of 8 base 10. Okay, base 10 again would be implied. As long as whatever log I'm doing the same base to the left as I am to the right. And if we go back to our previous rule property, if I have the log of 2 raised to the x power, then I know that I can take that x and that exponent, and I can bring it down in front. So that's the same thing as x times the log of 2 equaling the log of 8. And recall, log 2, log 8 are just numbers. They're ways of expressing those exponents. So I can divide both sides by the log of 2 to isolate my x variable. And I get x is equal to the log of 8 divided by the log of 2. Which, if I wanted to do a base change to base 10, right, we would have just switched it to the log of the 8 divided by the log of the 2 to the new base that we wanted. And in this case, we switched it to base 10. If I wanted to switch this to base E, right now this was base 2, this was base 10. If I wanted to switch this to natural log, then it would be the natural log of 8 divided by the natural log of 2. If I wanted to switch it to base 7, I would do the log of 8 base 7 divided by the log of 2 base 7. If I wanted to switch it to base 5, I could do the log of 8 base 5 divided by the log of 2 base 5. So whichever base you want, it's just you make sure that you're doing it to both the bottom and the top with that exact same base anytime you want to do a base change. All of these are equivalent. They all say the same thing. Okay? So let's look and do a few problems here. So if we want to simplify, we're going to get to solving equations, but prior to solving equations, we need to learn how to combine like terms, simplify quantities. So if I have the log of 70 minus the log of 7, I am subtracting 2 logs. subtracting two exponents, and we know if we're subtracting exponents, that means division with a common base was going on. Base 10 is implied on both of these. So if we have subtraction of two logs, that means that's the same thing as the log of 70 divided by the log of 70 divided by 7. Subtraction of logs, subtraction of exponents means division with a single log. And this is just the log of 10. And again, remember, base 10 is implied. So base 10 raised to what exponent gives us 10? And we know that is just 1. Okay. On C, I have addition of two logs, addition of two exponents. And we know if we are adding two exponents, that means that multiplication with a common base was going on. So I can think of this as the log base 3 of 108 times 3/4. And 108 times 3/4. Well, 4 goes into 108, 27 times? And 27 times 3 is 81. So we're really looking at the log of 81 base 3. And we know that's just asking us 3 raised to what exponent gives us 81, and that is just 4. I'm going to leave B and D for you to do, and we're going to look at E. Recall on E, you're plugging in a log base 2 into an exponential of base 2, and we know that if you combine a exponential and a log, they are inverses of each other. They're both base 2. Whatever you plug in, as long as it's in your domain, you're going to get out. So the left side is just 5. On the right side here, I have 3 log base 5 of 5 to the 1/3. I have a couple of options. If I want, I can take that 1/3 and bring it down in front and multiply. Or if I wanted, if I have the number in front of the word log, I could have taken that 3 and brought it back up as a power. Either one, both correct, whichever you like, or you could have even evaluated this log expression on its own. So you have lots of options, just like when we were working with Appendix B, we had a lot of options with our exponents. So I'm going to bring the 1/3 down in front and think of this as 3 times 1/3 times the log of 5 base 5, bringing that 1/3 exponent down in front of log. And I know then that's just my 1/3s are going to cancel, and I'm going to be left with 5 minus the log of 5 base 5. And we know that the log of 5 base 5 is just equal to 1, and 5 minus 1 is equal to 4. Okay, I'm going to leave 6A for you guys, and we will look at 6B. On 6B, we have a number of coefficients in front of the word log. So keep in mind, if we wanted to, we want to simplify these, and we want to try to simplify as far as we can so that we have just a single log. So if I look at, actually I'm going to go back to 6A, guys. If we have addition of 2 logs, we know if we are adding exponents, that means multiplication was going on. So inside our parentheses, that would be the natural log of 4 times 32. And 4 times 32 is 128. And if we have a number in front, a coefficient to our log, then we know that that means that that was or could have been a power, so we can bring that back up as an exponent. So now we are looking at, excuse me, the natural log of 3 minus the natural log of 128 squared. And if we have subtraction of 2 logs, that means that division with a common base, single log division was going on. So the natural log of 3 divided by 128 squared. And we just wanted to simplify to one word of log, and we are done. If we look at B, trying to simplify that, combine like terms, simplify so that we only have one word of log. If we start inside our parentheses here, we have a 2, coefficient of 2 in front of the word log that we will be able to bring up as an exponent. We have this coefficient of 6 in front of the log that we will be able to bring up as an exponent. We have this coefficient of 4 in front of that word of log that we will be able to bring up as an exponent. So we'll be able to bring each of those up. So initially, I'm going to have the log of 3 to the 4th minus the log of x squared plus 1 to the 6th plus 1/2 times the log of x plus 1 minus the log of 3 squared. Inside our brackets, we're subtracting 2 logs, same base, and subtraction of 2 logs with a common base. That means division was going on. So inside our brackets, we can think of that as log, base 10 has been implied, of x plus 1 divided by 3 squared. If I look at these two terms here, we also have subtraction of 2 logs, same base, which means if it was subtraction of 2 logs with the same base, that means we were looking at one word of log, and again, division, because we know that when we are dividing with one common base, we subtract our exponents. So we can go backwards, and the log of 3 to the 4th divided by x squared plus 1 to the 6th. And now here, we have a coefficient in front of that log, which means that that coefficient can come back up as an exponent around that quantity. So I'm going to now rewrite that. So we have the log of 3 to the 4th over x squared plus 1 to the 6th plus the log of x plus 1 over 3 squared raised to the 1/2. And lastly, if we are adding exponents, logs are a way of expressing those exponents, that means multiplication with a common base was going on. Again, we're still all working with base 10, so we can combine these to a single log. And we're looking at the log of 3 to the 4th over x squared plus 1 to the 6th times x plus 1 over 3 squared to the 1/2. And we know that here, the square root of the 3 squared, well, you could reduce that down to just a 3. So this part would reduce just to a 3. We would still have the x plus 1 of our 1/2, and then this 3 and our 3 to the 4th can reduce. And so our final answer would be the log of 3 cubed, or 27, over x squared plus 1 to the 6th, and then times our x plus 1 to the 1/2 for our final answer, where we have simplified that to just one word of log. Okay, let's look at number 7. Actually, let's hold off there, and then I will come back and do another video.